Papa Flammy's Advent Calendar.
Here.
Whee! Good morning, fellow mathematicians. Welcome back to another day of Papa Flammy's Advent Calendar. And I would like to continue with the quantum mechanics series. If you're wondering what I'm writing on, it's going to be the Gaumon PD 2200. The people from Gaumon were kind enough to sponsor this video a while back with this tablet, and if you're interested, you can find all the links down there in the description. Also, don't forget to check out STEM merch. Today we got 10% off the most beautiful equation in mathematics collection, the whole collection. Also, we got a lot of other STEM merch over there, as the name would suggest, like climb bottles, Newton's cradles, chaos pendulums, etc. And all the other like. Okay, check it out. And now we are going to dive into the main meat of the video. Namely, we would like to take a look at the probabilistic aspect of quantum mechanics today. It's just a little introduction to continuous variables basically in probability theory. We are going to start off with discrete models, and then we are just going to drag everything over to the continuous models, and they are going to be applied in quantum mechanics a lot, because quantum mechanics is just statistical interpretation of wave functions under certain potentials. Yeah, and this is what we are going to do now. Let's dive right in. So at first, let us start off with a very easy scenario. Namely, we are going to roll a die. Okay, just a single die, meaning if we were to sketch a die, it's going to look something like this. We are going to have 6 sides in total. We are going to say that it's a fair die. We're going to have 1 here, on the other side we have a 6, then a 2 up here and a 3 here. And now one could ask himself the question, what is the rate, the probability of getting each and every of this number? For example, with what likelihood can you roll a 6 on this die? People didn't know this a while back, but there is something called the law of big numbers that is going to tell us if you take infinitely many of those rolls with the die, you are going to see that it's going to converge to a certain probability to roll one of the 6 sides of the die. And we can actually simulate this using a little Python script I wrote ages ago. Okay, so with this very easy to write Python script, you can actually simulate number of rolls. I programmed this a while ago, it's not very efficient, but this really doesn't matter. We are going to say, okay, let's roll it 10 times at first. Let's see what the probabilities are going to be overall. Okay, probability to throw the 1 is 40%, to throw 3 0% at the moment, and to throw 6 also 0%, or 10% for 4 and 5. Now what about if we were to, let's say, throw 100 times? Let's say what the probability is then going to be. Okay, so the probability to throw either of those is, I don't know, it's going to go to 15% it seems. What about throwing this whole thing, let's say 10,000 times? Oh, they are all at 16 something percent. Could this be, okay, what about rolling it 1,000,000 times? They are all going to go to 16.6%. And this is not a coincidence. They are all going to converge to 16.66666%. This is exactly 1/6 of 100% per throw. And this is kind of curious, right? Let us put this into more mathematical terms. So at first we're going to write out the so-called sample space. It's basically the set of all outcomes, and it's being denoted by big omega. Meaning we are going to write it like this, and it's going to be the set of all the possible outcomes. Well, what can we roll with the die? 1, 2, 3, 4, 5, 6. Okay, we can roll all of those elements right here. And this set has a certain cardinality coming with it. The cardinality is just the number of objects in the space, namely the cardinality of our capital omega is going to be how many things have we in here? Oh, 6 elements. So we have 6 possible outcomes that could occur while rolling a die. And we are going to denote this cardinality of our omega with just capital N. Okay, this is the total number of outcomes in our system. Now, we could also count how often does each of the outcomes occur in our set. Okay, if we have a die, then on each and every side it only occurs once. Meaning, the number of rolling 1, okay, so the number of possibilities to roll the number 1 is going to be 1. That's the same as the number of possibilities to roll the 2, and that's the same as number of possibilities to roll 3, etc. up until n of 6. So what is the probability now in general to roll any side right here on this die? So what is the probability of rolling 1, 2, 3 or something? Well, if we take a look at the convergence here, okay, for infinitely many rows of the die, each and every one of those is going to converge to 1/6. Oh, 1/6. That is kind of curious. I mean, the total number of sides that we have, so the probability of rolling any of the sides is going to be something over 6. So this is something over the total number, so the cardinality of our sigma. But what is going to go up there in the numerator? Well, this is just either rolling 1, okay, so the number of possibilities to roll 1 or 2 or 3, etc. Meaning this is just going to be the number of ways to roll our event, basically our occurrence x in some way. So meaning overall, since our 6 was nothing but the cardinality, we are going to have in general that the probability of some event happening is going to be n of x divided by the total number of things that we have in our omega, so the total number of possible outcomes that we can have in the system. And just to make one thing a bit more clear, we can actually express our n that we're having up here, so the total number of things that could occur, using our n of x in some way. Namely, if you take a look, if we were to add all the n of x's together for the die, so all 6 possibilities which come at 1 per possibility, we are going to get the total number n up here, so the cardinality of omega. Meaning our n can actually be expressed as the sum of all, it really depends how many discrete variables you have or how many discrete samples you have. If you have infinitely many discrete samples, but countably infinitely many discrete samples, then we are just going to have that x is greater or equal to 0 up until infinity of our n-axis, okay? And in our case, with the die, it's only going to be 6 samples overall, or 6 possibilities. Hence the sum would go from 0 to 5 in our case, or from 1 to 6, really doesn't matter. Really depends on your shift of index. Now let us take a look at another example, because it could sometimes look a bit differently than just having a 1 up there in the numerator. Let's say we have an urn, okay? And in this urn we have, let's say, 2 balls of this color, and then we have 3 balls of this color. Now, what are the probabilities to, let's say, draw either of those? Okay. By our current understanding, we know that, for example, drawing green it is, I can tell the numbers, okay, drawing green. We are going to have that this is the number of how often green occurs in our urn, meaning this is going to be 2 times. 2 divided by, and how many balls do we have in total? 5. Okay, 2 5. And what's the probability of drawing, I guess that is blue? Well, we have 3 blue in there, divided by, well, once again, 5 balls in total. Yeah, those are our probabilities to draw those, and you see you don't have to have a 1 in the numerator. It could also vary from scenario to scenario, basically. Now I would like to go a step further with the urn scenario, because I would like to talk about something called tree diagrams, and they are going to be the motivation for what we are going to do next, namely the total probability in a system. So a tree diagram is basically just a very good visualization of for example, drawing cards or rolling a die one after another, of basically random events happening one after another, be it if they influence each other or not. Meaning a tree diagram, as the name would suggest, has certain branches coming with it. Namely, what possible scenarios can we have when drawing out of this urn? I mean, we can have 2 scenarios. You can, if you put your hand in there, draw a green ball, or you can draw a blue ball. Meaning it has 2 branches overall at first. One for the blue balls, and then the other one for the green ones. Okay, now what is the probability to draw either of these? I mean, for the blue ones, we know this is going to be 3/5, and you're going to put the probability right next to the branch. And for the green one, it's going to be 2/5. Now, let's suppose we are going to draw 2 balls out of the urn, and those balls will be put back, okay? So meaning, Those are independent from each other. We are going to grab a ball, take a look at it, and put it back into the urn, mix it up, and draw one again, and meaning we have drawn 2 times, but the total sample size is going to stay at 5, for example. Now, what can happen, what possible scenarios, after we have grabbed ourselves a blue ball? I mean, if we put it in there yet again, we can grab a blue ball again or a green ball. Meaning, we have 2 branches yet again. We have one with the blue ball, and then we also have one with the green ball. Now, what are the probabilities? I mean, the total number of blue and green balls really doesn't change, as well as the total number of balls in general. Meaning, it's going to stay at 3/5 on the left-hand side and at 2/5 on the right-hand side. Now, what about the other situation? We have drawn green at first, put it back. What can we draw now? I mean, once again, green and blue, and all the numbers stay how they were before. So meaning for blue we have 3/5 once again, and for green we have 2/5. And now here comes the first, in German it's called Pfadregel, it's probably called the path rule or branch rule, something like this in English. This is the first rule that applies for tree diagrams, namely, the probability for a certain scenario, for example drawing green at first and then drawing blue, can be found out by multiplying together all the probabilities on the path. Meaning, if we want to find out what the probability is of drawing 2 times green, on one branch, we are just going to multiply 2/5 and 2/5 together. Okay? Meaning overall you can say that the first rule just states along a path, we multiply. So let us go through a few different scenarios. Let's say we are going to find out the probability of drawing 2 times blue, for example. Okay, this is something that could happen, meaning we're going to multiply along a path. Okay, we are going to multiply 3/5 by 3/5, leaving us overall with 9/25. 9/25. Okay? This is just what's going to happen. Now what about drawing, let's say, green and after that green yet again? Meaning we are going to have the scenario of green and green, and per our rule we are just going to multiply 2/5 with 2/5 together. Meaning this is going to give us 4/25. Now what is the last possible thing that could happen? I mean, we could draw blue at first and then green, or we could draw green at first and then blue. They are both going to have the same probability because 2/5 times 3/5 is the same as 3/5 times 2/5. I mean, multiplication commutes. And now here comes the second path rule, and namely, if we want to find out the total probability for some certain event happening, for some scenario, we are going to add all the multiplied probabilities together. Meaning, we are going to say, let's say as a little example, we want to grab 2 times into the urn, but we want to find out the probability for drawing at least 1 blue ball in the process. So I've written everything out pretty quick. So second rule just states to get a total probability for a certain scenario, we add all the multiplied probabilities P together. And now our example is draw at least 1 blue ball when drawing 2 times in total. And with our rule and what we have found out before, so the first path rule, it's rather simple actually. Namely, drawing at least 1 blue ball also means that we can draw 2 blue balls, because at least means you can also draw more than that. Meaning we are going to add this probability to this probability and this probability. So the probability to draw at least 1 blue ball is 6/25. And this times 2, because we can either draw green at first or blue at first, and then we are going to add to it 9/25. So this makes 12 plus 9 is going to give us nothing but 21/25. I mean, I know you could also say this is like the complementary event of not drawing any blue ball at all. This is also something that you can say, but this would take away the point that I'm going to make now. Namely, you see we can calculate probabilities like this. Now, what is the total probability of drawing 2 balls when drawing 2 balls? I mean, we can just add all the possibilities or all the probabilities together that we have up here. Drawing 2 balls, when drawing 2 balls, means we are going to add 9/25 to 4/25 to 2 times 6/25, meaning overall, the probability of drawing 2 balls is nothing but, okay, we got 12 25ths plus 9 25ths plus 4 25ths, and overall this makes 25 25ths, which is nothing but 1 overall. Meaning the total probability of some event to happen, oh, okay, so something has to happen. If you draw 2 times, you draw 2 times, okay, you definitely draw 2 balls, it's going to result in 1. And this is something that is always going to apply. If you add all the probabilities together in a certain scenario, meaning adding all the probabilities together that go along one line basically on a tree diagram, you are going to get that this is going to result exactly in 1 overall. Isn't that quite interesting? Meaning, let us put this into mathematical terms. We now know that 1 is nothing but, and 1 is the likelihood, so 100%. Basically, this is why I said using the complementary event would take away from my point. 1 can be expressed as the sum of, okay, it really depends on the sample size you have. Let's assume we have infinitely many discrete variables yet again. P of x, the sum over all of these is going to result in 1 overall. And this right here is one of the most important points we are going to track over to the continuous variables in a few minutes from now. Next up, I would like to talk about the so-called expected value, or also called average or mean. And for this, I'm going to take an example that you are probably most familiar with. Namely, we are going to take a look at grades in a class. Here in Germany, grades go from 1 to 6. And let's say I have written a certain test with my students, and it looked like this. So all the grades together were distributed like this. So we got grades 1 to 6. Overall, and let's say no person had a 1, 1 person had a 2, and then 5 people had a 3, and then 2 people had a 4, 3 people had a 5, and 1 person had a 6. Now to calculate the average, okay, the average or the mean, we are going to proceed as follows. We are going to multiply the number of people with the certain event. Then we are going to add all of those possibilities together along this table, and then we are going to divide it by the total sample size yet again, meaning all those samples added together, all the grades, so the number of students in my room together. Let us do this really quick. So we got 0 times the number 1. I'm going to put this in parentheses. Then we are going to add to it 1 person got grade number 2. Then we are going to say 5 people got grade number 3, and so on. Now we are going to divide everything by the total number of people who participated in the test. Namely, we got, okay, this is 5, this makes 12 overall. Now you can feel free to calculate this, but the main point is that you can see the structure of how to calculate the mean overall. Namely, what we are going to do is to calculate the mean of a certain random variable happening or certain event happening. We're going to denote it with either E of x, okay, this is the expected value or the mean basically overall, but it's also called the expected value, really doesn't matter. We can also denote it like this. This is happening often in quantum mechanics with those sharp brackets basically. We are going to express it as follows. Namely, what we are having up here in the numerator is, okay, let's say we have an infinitely large sample size yet again. We are going to take the event, this is the thing that is in parentheses, so like the random variable happening. Okay, if we put this into dice notation, die notation, we could also say how often have we rolled the dice for each and every scenario. So we are going to add multiply x by, and okay, by what are we going to multiply it? I mean, by the number of samples rolled basically for the die, or by the number of grades per student basically. Meaning this is just going to be n of x yet again in the notation that we had before, and all of this divided by the total sample size, namely capital N. Now we can manipulate this a tiny little bit further, namely the sum, okay, the numerator is additive, meaning we can drag the sum to the front. And now what we are going to have is x multiplied by, oh, this is kind of curious, n of x divided by n. n of x divided by n is nothing but our probability of something happening. Isn't that interesting? So meaning the mean average expected value is going to be just the event happening multiplied by the probability of the event happening. It's as easy as it is. And this expected value, to put it in layman's terms, as the name would suggest, is just a measure of how expected an outcome of a random event could be. So if you're doing a lot of gambling, for example, or if you are someone who offers gambling to people, okay, for example on a carnival, then it's really beneficial to calculate the expected value in before to know how much money you're going to lose or how much money you are going to make, for example, or what the prize money of a certain event should be, such that you get the most income out on the other side for yourself if you're like the owner of a carnival shop. Now, next to the expected value, there's also something called the standard deviation and the variance. So we are going to denote the variance as being sigma squared, and you can also denote it by the variance of some event x. And basically, there's also something called the standard deviation. This is just sigma, so it's the square root of the variance. And the standard deviation basically tells you how much your data is going to stray apart from the expected value. So you expected a certain outcome to happen, and how much error or noise basically do you have in your expectation. Okay, this is basically what you could say it is for. And there's a very simple rule to get yourself the standard deviation. This is just how it has been defined. Namely, this is the square root of, and now we are going to take the expected value of an event squared, of a squared event, basically, minus the expected value of an event squared. Okay? Might sound kind of weird, but there's a result that you can basically derive from what we have up here with the expected value. Namely, if we have the expected value of an event squared, this is just going to be the sum, once again, over the squared of the event happening times the probability of the event happening. You can derive this, it's not too hard actually. And now that we are talking about that, you can also get yourself the expected value if you apply a function to this whole thing. So to get the expected value of a function, okay, you are just going to basically plug the function into your x on the right hand side. This is just something that holds. And we are going to use this later extensively because we are going to deal with wave functions in quantum mechanics, and you need some kind of function to calculate the probability on. So it's really useful, don't forget that. Now that we are done with those basics, with the discrete variables basically, we are going to go over to uncountably infinite discrete variables, also called continuous variables. And this is really important because we are going to take a look at continuous wave functions in quantum mechanics. Let me write everything out and then we're going to transfer everything to continuous variables. So I've written everything out, and the continuous counterparts are extremely similar to the discrete ones. Namely, what we are basically going to do is we are going to say, okay, an infinite series is basically nothing but an integral. I mean, there has always been this approximation that like the summation, the infinite series, is less or equal to an integral with the same basically summand or integrand or sequence in there. And we are going to go by the same means. Meaning if we have, for example, a wave function, okay, something like this. This is a wave function that we are going to have. And we want to calculate the probability of something happening in a certain interval. Okay, let's say from A to B right here. We are going to say that the continuous probability basically on the interval a to b can be defined as the integral from a to b of just a function f of x dx, okay, integrated, where our function could be, for example, our wave function. Now the same thing applies for the number 1. This is extremely important with the number 1 because this is called normalization. We always, since we are dealing with partial differential equation, get some constant out when dealing with the wave function. This constant we can find out by putting it into the normalization process. We need to normalize the wave function such that it makes physical sense. If a probability to find something outside of classical region, for example, would be greater than 1, that wouldn't really make any sense because you can't have a probability that is greater than 1, not in the classical sense. Meaning 1 in our case can be defined as being And this is the integral over the whole of R, basically over the whole real number line. We want to normalize it over the whole interval in the real number line from negative infinity to infinity of f of x dx yet again. Put your wave function into here and find out your constant a, which is the normalization constant. Now next up is the expected value, the average, the mean, whatever you want to call it. I'm a mean guy, we're going to go with mean right here. You can go by the same means yet again. We're going to define it from negative infinity to infinity as an integral of just x multiplied with f of x dx. Okay, and this is how you calculate the mean value. You can also do so for functions. Let's say we're going to find out the mean of the function g of x. Just put it into the place where our x was before. Namely, we're going to get g of x, f of x, and then dx. And last but not least, what about the standard deviation? Well, it just stays how it is. The standard deviation, there is nothing you could really change. If you want to find out the standard deviation, you are just going to plug basically your expected values in, and then you are done. Next, we are going to talk about a real quantum mechanical system, probably the quantum mechanical harmonic oscillator. Also, I'm going to talk about square integral functions, because in normal case our wave functions are going to be complex valued functions. And we get a problem if we want to find out, for example, the probability on an interval AB of a complex valued function. To get rid of this, we are going to get ourselves basically the modulus of this complex value function and square it, meaning it's the square root of a complex number squared, giving you basically just a real number, or just a magnitude basically in the real plane. Yeah, so this is what we are going to talk about next. I think that's watching. If you enjoyed this video, thanks for subscribing to the channel. I want to support you. And up until next video, guys, a flammable day. Ciao.